Somewhere above you tonight, if the sky where you are is clear, there is a star. Just one, to start with. Pick any of them. A small, steady point of light that has been travelling toward you for years, sometimes for centuries, before slipping in through your window or brushing the edge of your vision on a walk home. And here is the strange little thing I want to sit with you and turn over slowly tonight. That point of light is not really steady at all. It shimmers. It flickers, very faintly, in a way your eye can barely catch, the way a distant street lamp seems to tremble on a warm night. And buried inside that shimmer, hidden in the tiny, restless flicker of a star, there is a number, the star's true size, its actual width, across all that impossible distance. And the astonishing part, the part that took some of the cleverest people of the last century, the better part of 50 years to believe, is this. You can read that number without ever making a picture of the star, without a telescope sharp enough to show its disk, without seeing anything at all except how the light shimmers. Let me show you the trick, gently, because it really is a beautiful one. Imagine two detectors, not two telescopes trying to take a photograph, just two light buckets, two eyes if you like, set some distance apart on the ground. A few meters, maybe, and both of them are pointed at the very same star. Neither one is trying to see any detail. Each one is doing something almost childishly simple. It's just watching how bright the star is, moment to moment, and noticing that the brightness isn't perfectly constant. It wavers, it flickers up and down, a little, all on its own. Both detectors watch the same star flicker, and each writes down its own little record of the shimmer, its own private list of the tiny ups and downs of the light. And then you do the one thing that makes the whole magic trick work. You lay those two records side by side, and you ask a single question. Did they flicker together? When one detector saw the star brighten for an instant, did the other one, a few meters away, brighten at the same instant too? Or were they doing their own separate things, one going up while the other went down? Two people humming two different tunes? Here is the quiet miracle. When the two detectors are close together, the two shimmers keep in step. They rise and fall almost as one, like two friends who've walked side by side so long they've fallen into the same stride without noticing. And as you slide the two detectors farther and farther apart, that agreement, that lovely in-stepness, very slowly comes undone. The two shimmers begin to drift, to disagree, to lose the thread of each other's rhythm, until at last, at some particular separation, they've wandered so far out of step that comparing them tells you nothing at all. They've become strangers. And that distance, that exact separation, the one where the two flickers finally stop agreeing, where they slip loose from one another for good. That distance is the ruler. That is the number. Read how far apart you had to pull the two detectors before the shimmers came apart, and you have measured, with nothing but flicker and patience, the true width of a star. Close together, they flicker as one. Pull them apart, and the agreement dissolves. And the precise distance at which it dissolves is set entirely and only by how big the star really is. Don't worry if that doesn't fully land yet. It isn't supposed to, not on the first pass. We have a long, slow night ahead of us, and we're going to walk into every corner of this idea, one soft step at a time. So let it just sit there for now, that lovely, unlikely picture. Two eyes on the ground, a distance apart, both watching one star shimmer, and the secret of its size hidden not in the light itself, but in how well the two shimmers keep each other company. Welcome to the Curious Voyager. It really is lovely to have you here tonight, wherever here happens to be for you. Maybe you're lying in a dark room with the blankets pulled up and one lamp still glowing somewhere near the door. Maybe you're on a train, forehead against the cool glass, the world sliding by in the dark. Maybe it's the middle of the afternoon and you just need somewhere quiet to put your mind down for a while. However you've arrived, I'm glad you did. And I'd genuinely love to know if you feel like leaving a little note somewhere down below before you drift off. Where in the world are you listening from tonight? And what time is it in your corner of the dark? It's a small thing, but I like imagining all of us scattered across the world, in all these different pockets of night, listening to the same quiet story about a star. And if you find you enjoy these slow journeys, a gentle like and a subscribe really does help this sleepy little channel keep going. I'm a small creator, and honestly, that quiet support means more than I can easily say. So if it isn't too much trouble, it would mean a great deal. And to those of you who've already subscribed, who come back night after night, thank you. Truly, you're the reason there's a voice here at all. Now here is the promise I want to make you, and then I'll ask nothing else of your attention for the rest of the night. We are going to move slowly. Slower than you might expect. There is no rush here, no ground we have to cover, no test at the end. If your mind wanders off partway through and you lose the thread, that's not a problem. That's the whole idea. The star will still be there, the story will still be here. You can drift off in the middle of a sentence and none of it will be lost, because we're going to circle back and around the same few beautiful ideas so many times, so gently, that whichever piece you happen to be awake for will make its own quiet sense. You don't have to understand everything. You don't have to hold on to any of it. You don't even have to stay awake. If sleep comes for you before the end, let it. That's a good ending too. Maybe the best one. So, let's begin properly, shall we? And to begin, I have to tell you why what I just described sounds, at first, completely impossible. Because to really feel how clever this trick is, you have to first feel how stuck everyone was without it. Here is the problem, and it's a problem that tormented astronomers for a very long time. The stars are far away. You know this, of course, but I mean it in a very particular, very awkward way. They are so far away that even the biggest of them, the great swollen giants, the ones that dwarf our own sun so completely that it would be lost inside them like a marble in a cathedral, even those appear, from here, as nothing, as a point, as a single dimensionless dot of light with no width to it at all. Let me try to give you a feel for how small a star looks. Astronomers measure the apparent size of things in the sky, not in miles or meters, because a thing's real size and its distance get tangled up together. A far-off mountain and a near-off pebble can look exactly the same size held up against the sky. So instead, they measure the angle a thing takes up, how wide it looks, how much of your view it fills. The full moon, for instance, takes up about half a degree of sky. Hold your little finger up at arm's length, and its width covers roughly a degree, roughly 2 full moons side by side. That's the scale we live at with our eyes. Now 1 degree can be sliced into 60 smaller pieces, and each of those is called an arc minute, a minute of arc. And each arc minute can be sliced again into 60 smaller pieces still, and each one of those is called an arcsecond, a second of arc. So an arcsecond is a 60th of a 60th of a single degree, a tiny, tiny sliver of sky. To picture 1 arcsecond, imagine looking at a small coin, and then walking away from it, and walking, until the coin is about 5 kilometers away, 3 miles or so, a distant invisible speck across a whole city. The angle that far-off coin makes in your eye, that's roughly 1 arcsecond, impossibly small already. And here is the cruel joke of it. The stars are smaller than that, not a little smaller, much smaller. Even the largest stars in our sky, measured as an angle, come in at hundredths of a single arcsecond. Take that coin that was already 3 miles away, that tiny invisible speck, and now imagine trying to make out not the coin, but something 100 times finer still. That's the width of a star. That's the disk you'd need to see to measure it directly. So, of course, you might think, well, that's what telescopes are for. Build a bigger telescope, a sharper one, and zoom in until the point becomes a disk, until you can see the star's actual round face, and just measure it with a ruler laid across the picture. It's a completely reasonable thought, and it runs straight into a stone wall, for 2 separate reasons, and I want to give you both slowly, because together they're what made the whole thing seem hopeless. The first wall is the air, our own atmosphere. That same blanket of air that keeps us warm and lets us breathe is, for an astronomer, a maddening, shifting veil of trouble. The air above your head is never still. It's full of currents, warm pockets rising, cool pockets sinking, little rivers of moving air all stacked on top of each other, all bending the starlight this way and that as it comes down through them, each pocket acting like a wobbling, imperfect lens. This is why stars twinkle. That pretty, romantic twinkle you see on a clear night, that's not the star doing anything at all. That's just its light being jostled and nudged around by kilometers of restless air on the very last leg of a journey that took years. The star is steady. The air is not. And for the astronomer trying to measure a star, that twinkling, shifting air is a disaster. It takes the sharp point of starlight and smears it out, blurs it, spreads it into a little dancing, trembling blob. Astronomers have a word for how badly the air blurs things on a given night. They call it the seeing. And on a good night, at a good sight, the seeing blurs a star out to about 1 arcsecond across. 1 whole arcsecond of smear. Now hold that up against what we said the star actually is. The star's true angular size is hundredths of an arcsecond. But the air smears it into a blob, a full arcsecond wide, 10 times, 50 times, 100 times bigger than the star itself. It's as if you were trying to measure the exact width of a single human hair, but every time you looked, the hair had been swollen and blurred into a fuzzy rope as thick as your wrist. The real thing, the thing you actually want, is buried somewhere deep inside a blur 100 times its own size, and the blur is dancing, changing shape 100 times a second. You could point the finest telescope ever built at that star, and the air alone would rob you of the disk. All you'd ever catch is the trembling blob the atmosphere hands you. But suppose, you might say, suppose we get above the air. Put the telescope on a mountaintop above most of the weather, or up in space entirely, where there's no atmosphere at all to blur anything. Surely then, with the air out of the way, we could just zoom in and see the disk. And that brings us to the second wall, and this one is deeper, because this one is built into the nature of light itself, and you cannot climb above it or fly past it. It would be there even in a perfect vacuum, with a perfect mirror, in the stillest, clearest emptiness imaginable. Light is a wave, and waves, all waves, have a habit that turns out to matter enormously here. When a wave passes through an opening or bounces off the edge of a mirror, it doesn't travel in a perfectly clean, infinitely sharp line. It spreads. It fans out a little at the edges. You've seen this with water, ocean waves bending and spreading as they squeeze through a gap in a harbour wall. fanning out on the far side into gentle curves. Light does exactly the same, only on a scale far too small for your eye to notice in daily life. This spreading has a name. It's called diffraction, and it means that when any telescope, however perfect, gathers the light of a star and brings it to a focus, that light does not arrive as an infinitely fine point. It arrives unavoidably as a small, soft, fuzzy little smudge with faint rings around it, a smudge whose size is set by the size of the telescope's mirror and by the wavelength of the light itself. This is called the diffraction limit, and it is the hard floor, the absolute sharpest a telescope of a given size can ever possibly be, even in a perfect universe with no air at all. And for a star, for those hundredth of an arcsecond widths, the diffraction smudge of any ordinary telescope is again far larger than the star. So even lift yourself clear of the atmosphere, even build a flawless mirror in the silence of space, and light's own gentle refusal to be a perfect point defeats you all over again. The star is still smaller than the smallest smudge your instrument can make. It is still, stubbornly, hopelessly, a point. So sit with where that leaves us, because this is the wall that the whole story is trying to climb. Here is a question that seems, on its face, perfectly fair and perfectly answerable. How big is that star? And here is the answer physics keeps handing back for decade after decade. You cannot see. There is no disk. There is no picture to measure. The star shows you nothing but a point of light, and no telescope, on the ground or above it, can turn that point into a face. The size is there. The star has a real width, a real diameter, a real edge somewhere out in the dark. But it seems to be information the universe simply refuses to give you, a locked room with no door. And this is the moment I want you to feel, half asleep or not, because everything beautiful that follows grows out of it. The problem looked closed, not hard, closed, the kind of problem where the sensible thing to do is shrug and admit some things just can't be known, and move on to easier questions. For a long stretch of the early 20th century, that's roughly where things stood. The stars kept their sizes to themselves. But there was a crack in the wall, a very subtle one, easy to miss, and finding it meant asking a stranger, sideways sort of question. Not how do I make a sharper picture, which is what everyone had been asking, but something quieter. If the star won't give me a picture, is there anything else it gives me? Is there some other quality of the starlight, some other fingerprint riding along in it, that still carries the width even when the picture is gone? And there is. There truly is. And to reach it, we have to talk, softly, about a property of light that has nothing to do with how bright it is, or what colour it is, or how sharp a picture you can form from it. A property called coherence. Let me walk you into that word gently, because it's the hinge the whole night turns on, and I don't want to introduce it with a definition and leave you cold. I want you to feel it first. Think about a wave again. Light is a wave, remember, a rippling, a rising and falling, a crest and a trough, marching along, over and over, incredibly fast and incredibly small, but a wave all the same. Now imagine you have 2 points in space, 2 little spots where you could stand and watch the light wave go by, feeling it rise and fall, crest and trough, crest and trough. And here's the question coherence asks. If you watched the wave at both spots at once, would the 2 of them be marching in step? When the wave crests at one spot, does it crest at the other too? Do they keep the same rhythm, the same beat, so that knowing what the wave is doing at one place lets you know what it's doing at the other? If so, we say the light at those 2 points is coherent. They're in tune. They share a rhythm. And if instead the 2 spots are doing their own unrelated things, cresting and troughing with no relationship at all, 2 dancers ignoring each other entirely, then the light there is incoherent. Out of tune. Strangers, again. Now here is the lovely, deep fact, the one that cracks the locked room open. Whether the light from a star is coherent across 2 points on the ground, whether those 2 spots share a rhythm or not, depends on how big the star is, and it depends on how far apart the 2 points are. The 2 things are tied together, braided into one relationship, and inside that relationship, quietly, is the answer we thought we could never have. Let me try to give you a feel for why the star's size should have anything to do with this at all, because it's one of those things that seems like it couldn't possibly be connected, and then, once you see it, feels almost inevitable. A star is not really a single point of light, of course. It only looks like one from here. In truth, it's a vast, glowing ball, and every little patch of its surface is shining on its own, sending out its own light, its own little wave, all of them independent, all of them glowing away, with no coordination between one patch and another. The star is like an enormous crowd, millions upon millions of tiny lamps, each one flickering to its own beat. And what reaches you is all of their light mixed together, blended into the single point you see. Now, when all of that light, from all across the star's face, arrives at 2 spots on the ground that are very close together, something gentle happens. Because the 2 spots are so near each other, the light from every patch of the star reaches them by almost exactly the same path, almost exactly in step. The whole jumbled crowd of the star's surface still manages to arrive at both close-together spots, keeping nearly the same rhythm, because there's simply no room in that tiny gap between the 2 spots for the different paths to fall out of line. So the light at 2 nearby points stays coherent, in tune, in step. But now, very slowly, pull the 2 spots apart, widen the gap between them. And now the light from one edge of the star and the light from the other edge of the star start to arrive at your 2 spots along noticeably different paths. One path a touch longer, one a touch shorter, and those little differences begin to scramble the rhythm. The crowd's blended light no longer arrives in the same beat at both spots. The tune starts to come apart. The coherence begins to fade. And the wider the star, the more spread out its glowing crowd, the smaller the gap you have to open before the rhythm falls apart. Because a bigger star has edges farther from its centre, longer path differences, more scrambling. A big star loses its coherence over a short distance. A small, point-like star holds its coherence over a much wider distance. Because its light all comes from so nearly one direction that the paths barely differ no matter how far you spread your 2 spots. Do you feel the trick reassembling itself now from a completely different direction? There is a distance, a certain separation between 2 points on the ground over which the starlight stays in tune with itself. Astronomers call it, roughly, the coherence patch, or the coherence length of the light. A wide patch means a small star. A narrow patch means a big one. And so, if you could only find a way to measure that patch, to find out how far apart 2 points can be before the starlight there falls out of step, you would be measuring the size of the star. Without a picture, without a disk, without ever beating the atmosphere or the diffraction limit at their own game. You'd have gone around the wall instead of over it. And that is exactly what both halves of tonight's story are secretly doing. though they do it in two wildly different ways that split some serious physicists into arguing camps for years. Both methods are, underneath, measuring that same coherence patch. Both are asking the same quiet question: over what distance does the starlight keep its rhythm? They just listen for the rhythm in two utterly different ways, and one of those ways was so strange that respected people swore it couldn't work at all. We'll get there. Slowly, I promise. But before we meet either of them, I want to give you the piece of mathematics that sits underneath all of it, holding the whole idea up. Because it's genuinely beautiful, and I think it's the kind of thing that's nicer to fall asleep knowing exists than to fall asleep never having heard. It has a long, gentle-sounding name: the Van Sittert-Zernike theorem. Don't let the name worry you. It's just two people's names, a Dutchman named Van Sittert and another named Zernike, stitched together the way these things often are. And behind the grand sounding label is an idea you can almost hold in your hand. The theorem says this: if you take the pattern of coherence across 2 points, how the starlight's in stepness rises and falls as you move those 2 points closer together or farther apart, that whole pattern is mathematically tied to the shape and size of the source, the star, by a particular kind of relationship. And the relationship is one that turns up all over physics and music and sound and light, a relationship called a Fourier transform. Let me decode that gently too. A Fourier transform is at heart just a way of translating between two languages that describe the same thing. On one side you have a shape, or a picture, or a sound spread out in space or time. And on the other side you have that same thing described entirely in terms of rhythms and patterns, of how much of each different scale, each different spacing, it contains. It's like the difference between hearing a chord and listing the individual notes inside it. The chord and the list of notes are the same chord. The Fourier transform is just the act of going from one description to the other, from the blended whole to the pattern of ingredients, and back again. And what Van Sittert and Zernike are telling us is astonishing when you sit with it. The pattern of coherence, the way the starlight's in stepness changes as you widen the gap between two detectors, is the Fourier transform of the star's own brightness, of its shape spread across the sky. The two things are the same information, written in two different languages. On one side, the star's true face, its size and shape, which you cannot see because there's no disk. On the other side, the coherence pattern, how the light's rhythm holds and fades across the ground, which you can measure, because it's spread out right there at your feet, as wide as you care to place your detectors. And the Fourier transform is the dictionary between them. Measure the one, translate it, and you have the other. So the locked room turns out to have a door after all, just not where anyone was looking. The star's width was never really hidden. It was written all along in a language nobody had learned to read, spread across the coherence of the light itself, waiting on the ground to be measured. You don't have to see the star's face. You only have to measure, patiently, over what distance its light keeps in tune with itself, and then let the mathematics translate that distance back into a diameter. The size was in the light the whole time, just not in the picture, in the rhythm. And this is where our two travellers, decades apart, come to the same wall and each find their own way around it. Both of them accept, from the start, that they will never see the star's disk. Both of them decide to measure the coherence patch instead, to read the rhythm rather than the picture. But how do you actually measure whether starlight is in step with itself across 2 points on the ground? What do you physically build? What do you catch? And how do you catch it? The first answer: The older one, the one that came first and nearly broke the people who built it, was to catch the light waves themselves from 2 points and physically bring them together and let them overlap, so that if they're in step, they reinforce, and if they're out of step, they cancel, and you read the coherence directly from whether the combined light brightens or fades. It's the obvious way, the honest way, the way you'd probably invent yourself if you sat with the problem long enough. And it worked, just barely, for a precious handful of the very largest stars, in the hands of a man who had already spent his life doing impossible things with light. But it fought the atmosphere for every measurement, and the atmosphere fought back, and for most of the sky it simply couldn't win. And the second answer, the one that came half a century later and sounds, when you first hear it, like it cannot possibly be true, was to throw the light waves away entirely, to not combine them at all, to just point 2 separate detectors at the star, let each one measure only how the brightness flickers, keep no rhythm, catch no waves, and then compare the 2 flickers afterward, on paper, on a wire, in a machine, long after the light itself is gone, and to find, impossibly, that the answer was hiding in there too. That second idea is where the ridicule lives. That's the one the serious physicists said broke the laws of nature. And they had a real argument, a good one, not the foolishness the legend likes to pretend. But before we can feel why they were so sure it was impossible, and why they turned out to be wrong in a far more interesting way than anyone expected, we have to go back to the first traveller, back to a mountaintop in California and a beam of steel bolted across the front of the great telescope of its age, and a man standing in the cold trying to hold 2 paths of starlight steady to within a fraction of the width of a single wave, while the whole restless ocean of the air above him did everything it could to shake them loose. Albert Abraham Michelson had already done impossible things with light for most of his life before he stood on that mountain. He had measured the speed of light with a precision that left the rest of the world blinking. He had, with a colleague named Edward Morley, built the most sensitive interferometer anyone had ever seen, and used it to look for the motion of the Earth through the ether. The invisible medium everyone assumed light had to travel through, and he had found nothing, absolutely nothing, a null result so clean and so carefully repeated that it eventually helped dissolve the ether idea altogether, though Michelson himself was never entirely comfortable with what his own experiment had done. He was a meticulous, slightly impatient man who preferred the precision of light over the untidiness of theory, and he had spent decades learning, with a craftsman's slow intimacy, exactly what light would and would not do. So when he turned his attention to the stars and to the question of whether any of them had a measurable width, he was not simply curious, he knew exactly what the problem was. He had understood since the 1890s that the answer, if it existed at all, was going to live inside the behaviour of light waves, in the patterns they made when they interfered with each other. And he had understood, with that same precision, just how hard it was going to be to read it. The idea is not complicated to state, though it takes a moment to settle into. When 2 waves arrive at the same point from slightly different angles, they can interfere. If their peaks line up, they reinforce each other, and the light gets brighter. If a peak meets a trough, they cancel, and the light goes dark. Alternate bright and dark, those are interference fringes, and a screen held in the right place shows them as fine stripes. You will have seen something like this if you have ever looked at the coloured rings in a soap bubble, or the patterns that water waves make when 2 stones are thrown close together. The fringes are the light writing its own geometry on the screen, recording the angle at which it came. Now, a single point of light infinitely far away, a mathematical star with no width at all, sends perfectly parallel waves. They arrive in perfect step. The fringes it produces are razor-sharp and perfectly stable, no matter how wide apart you place the two slits or the two mirrors that collect its light. But a star with real width is not one point. It is a disk, even a very tiny disk, made of thousands of overlapping point sources, each at a slightly different angle. Each of those points makes its own fringe pattern, shifted slightly sideways from the others. Stack all those shifted patterns on top of each other, and the stripes start to blur. The bright lines partially fill the dark lines in. The contrast, the visibility as it's properly called, goes down, and when the two collecting mirrors are moved far enough apart, the disk is wide enough in angle relative to the separation that all those individual fringe patterns cancel each other out perfectly, and the fringes disappear entirely. The contrast drops to zero. The baseline at which the fringes vanish for the first time is directly related to the star's angular size. Specifically, for a uniform disk, the fringes go dark when the baseline is approximately equal to 1.22 times the wavelength of the light divided by the angular diameter of the star. A bigger star, wider on the sky, kills the fringes at a shorter baseline. A smaller, more distant star requires you to push the mirrors further apart before the fringes blur out. Measure the baseline at which the fringes vanish, and you have the star's apparent width. This is what Michelson understood. And this is why, in the first years of the 20th century, he started thinking about how to build a device that could do it. The difficulty was already plain to him. To see the fringes from a star, you had to collect light from two separated points, two mirrors, two slits, two apertures, and bring those two streams together to mix them, to let them interfere. And for the fringes to be sharp, the path each stream travels from its mirror to the mixing point had to be equal to within a small fraction of the wavelength of light. For visible light, that's a fraction of a wavelength, somewhere around 400 to 700 nanometers. A nanometer is a billionth of a meter. You are trying to hold two separate optical paths equal to within something like 50 nanometers or 100, while building a structure large enough to span, eventually, tens of meters. And you are doing it on a mountain, at night, with the air above you doing what the air always does. Moving, he built his first proper stellar interferometer in 1920, working with Francis G. Pease at Mount Wilson Observatory in California, high in the San Gabriel Mountains above Pasadena. The instrument was attached to the front end of the greatest telescope then in existence, the 100-inch Hooker telescope, its mirror more than 2.5 meters across, the largest single piece of ground-based optical glass in the world. They bolted a steel beam across the top of the telescope, roughly 20 feet long, about 6.1 meters, and at each end of the beam they mounted a flat mirror. Those two outer mirrors caught the incoming starlight and redirected it inward to two inner mirrors, which then sent the combined light down into the telescope itself and onto the detector. The star's light was entering the device from 2 points, 6 meters apart, and those two streams were walked along separate paths of carefully matched length until they arrived at the same focus and made their fringes. The fringes were visible as they moved the inner mirrors, the path lengths could be adjusted, and you watched the contrast change. Crisp alternating stripes, or a pale wash. When the stripes were sharp, you had fringes. When they blurred to nothing, you had found the baseline that killed them, and from that you read the angular diameter. On the 13th of December 1920, Michelson and Pease pointed this apparatus at Betelgeuse. Betelgeuse, the great red star in the shoulder of Orion. You will know it if you have ever looked south on a winter's night in the northern hemisphere, a distinctly orange red light, one of the brightest in the sky, and slightly irregular in its brightness in a way that seems to breathe with the seasons. They moved the mirrors until the fringes washed out, and they read the baseline, and they calculated an angular diameter of about 0.047 arcseconds, less than 1/10 of a thousandth of a degree. A disk so small that a human eye could not come anywhere close to seeing it, and yet big enough, in angle, for Michelson's device to feel its width. And when they converted that tiny angle to a physical size, using the distance to Betelgeuse, which was known well enough, the number that came out was staggering. Something of the order of 300 million miles across. Larger than Earth's orbit around the Sun. You could take the Earth and the Sun and all the space between them, and tuck the whole arrangement inside Betelgeuse with room to spare. If Betelgeuse were placed where the Sun is, the Earth would be below its surface. It was the first direct measurement of any star's diameter, not an estimate from brightness and temperature and a guess about how stars work. A measurement. A ruler held up to the sky, reading an actual width. It is one of the cleanest moments in the history of measurement. They had done what looked impossible, and they had a number. But the atmosphere had made it hard. You can feel it even in the published accounts. The fringes flickered. The air over the San Gabriel Mountains is not still. It bends and shifts and curls in tiny eddies that change faster than a human can blink, and each shift moves the two optical paths by a fraction of a wavelength, enough to jiggle the fringes, to make them dance on the detector, to keep them from holding still long enough to measure comfortably. The astronomer is watching a pattern that slides and shimmers while they are trying to judge its contrast. It is like trying to read a page while someone shakes it gently and continuously in front of your face. For Betelgeuse, it was just barely manageable. Betelgeuse is vast by stellar standards, and so its fringes vanish at a relatively modest baseline. The 6-meter beam was enough. But Michelson knew that for smaller stars the fringe would only die at a much longer baseline, and building a longer beam meant more structure trembling in the wind and more chance for the atmosphere to ruin everything. He and Pease eventually built a 50-foot beam, a little over 15 meters, and used it on a handful of other very large, very close red giant and supergiant stars. Antares in Scorpius, Arcturus, the golden star high in the northern spring sky, Aldebaran, the red eye of Taurus, a few others. And that was all. The list stopped there. Those are among the largest stars in angular size on the entire sky. The method could not reach further. Hot main sequence stars, the ordinary blue and white stars that make up the great blazing body of the Milky Way. The ones whose temperatures and sizes nobody had ever directly measured, subtend angles far smaller than any red giant, angles that would require baselines of hundreds of meters to kill the fringes, and building a rigid steel beam hundreds of meters long, balanced on a telescope, trying to hold two optical paths equal to 50 nanometers, while the mountain wind blows and the temperature changes. Through the night, it was not merely difficult. It was, as a practical matter, beyond what anyone could do. So the sky stayed mostly unmeasured. Dozens of the nearest and brightest blue stars in the sky had angular diameters that nobody knew. The atmosphere had won. It would keep winning for another 3 decades. And the next attempt on the problem would not come from an optical astronomer at all, or from anyone who had been trained in the tradition of Michelson's fringes. It would come from a man who spent his early career not looking at stars, but listening to them. Robert Hanbury Brown grew up in England, trained as an electrical engineer, and spent the Second World War working on radar. Radar is a technology of signals. You send a pulse out, it bounces off something, and you catch the echo and read the time delay. The war taught an entire generation of British scientists and engineers to think in terms of signals, how they travel, how they corrupt, how they can be processed, compared, and read. When the war ended, Hanbury Brown brought that way of thinking to astronomy. He became a radio astronomer, which in the late 1940s was itself a brand new thing. The sky looks quite different at radio wavelengths than it does in visible light, and some of the brightest radio sources in the sky are not things you can easily see optically at all. They are radio galaxies, supernova remnants, dense clouds of hot gas, objects that broadcast powerfully at wavelengths measured not in nanometers, but in centimeters and meters. Two of the most powerful radio sources in the sky are Cygnus A and Cassiopeia A, both in the northern sky, and both intensely bright at radio wavelengths. Astronomers in the late 1940s wanted to know how big they were. Were they compact, almost point-like, or were they spread out across the sky? The answer mattered because it bore on what kind of object they were, how far away, how physically large in space. And here, at radio wavelengths, the problem of making an interferometer to measure an angular size had a different character. The wavelengths are so much longer, centimeters rather than nanometers, that the required path stability is far, far less severe. You are not trying to hold a path to 50 nanometers. You can tolerate errors many thousands of times larger. And the atmosphere at radio wavelengths is, relatively speaking, much better behaved. Radio interferometry was therefore a growing, practical, productive field by the early 1950s, extending baselines to hundreds of meters or even kilometers. But there was still a problem. To make interference fringes from two separated radio antennas, you had to physically connect them, run a cable between them, or use some other means to combine their signals coherently. Preserving the exact phase of each. That was expensive, technically demanding, and set an upper limit on how far apart the antennas could practically be placed. You could not just set one up in England and another in Australia and run a cable between them. And it was while thinking about this problem, how to measure the angular sizes of Cygnus A and Cassiopeia A when conventional radio interferometry could not easily reach the baselines needed, that Hanbury Brown and the mathematician Richard Twiss began working together. Somewhere around 1949 to 1952. And the idea they had was this: instead of combining the signals from two antennas in real time to look for interference fringes, what if you just recorded the way the intensity, the brightness, fluctuated at each antenna separately, and then compared those fluctuations afterward? This sounds like a modest variation. It is not. It is a fundamentally different kind of measurement. When radio waves from a distant source arrive at two separated antennas, both antennas pick up the same underlying radiation field, but each measures a total intensity, a total power, that depends on many wave components adding together. The intensity fluctuates over time because the source itself is not perfectly steady, and because the wave components drift in and out of alignment. The key insight, and this is the thing worth holding quietly for a moment, is that those intensity fluctuations at the two separated antennas are not independent. They are related. They carry a memory of where they came from. If the two antennas are close together, They are sampling nearly the same patch of the incoming wave front, and so the intensity fluctuations they see will be nearly identical. They will flicker up and down almost in sync. But as you move the antennas further apart, they start sampling different patches of the wave, patches that have drifted out of step with each other. And the correlation between their fluctuations begins to fall. And the distance at which the correlation has fallen by a characteristic amount is set, just as the fringe visibility was set in Michelson's instrument, by the angular size of the source. The mathematics was already known, at least in outline. It connects back to the same underlying theorem, the van Sittert-Zernike theorem. That links the coherence of a wave field to the Fourier transform of the source's angular brightness distribution. Michelson had been measuring one kind of coherence, the coherence of the field amplitude. Hanbury Brown and Twiss were going to measure a different kind of coherence, the coherence of the intensity fluctuations. But the angular size of the source was written into both. They worked out the radio version, confirmed it made sense mathematically, and it proved itself in practice. The correlation technique worked on Cygnus A and Cassiopeia A, giving angular sizes for sources that the phase-sensitive interferometers of the time could not easily reach. The technique was not just an idea, it was a tested, working method, with measurements behind it. And so when Hanbury Brown turned his attention back to visible light, back to the optical problem of stellar diameters that Michelson had left half-solved, he did so not as a man trying something new and untested, but as a man taking a technique that already worked and asking whether it could be ported into a different frequency range. The port was not trivial. Radio waves and light are both electromagnetic radiation, but the detection technology is utterly different, and the timescales involved are faster by many orders of magnitude. A radio receiver records the signal as a varying voltage, and you can sample it with electronics that respond on timescales of nanoseconds. Light arrives at photomultiplier tubes, devices that convert individual photons or streams of photons into electrical pulses, and the correlations you are looking for in the intensity fluctuations happen on very short timescales, governed by the coherence time of the light, which for a filtered spectral line is on the order of nanoseconds or shorter. It was not obvious, before you tried it, whether the electronics of the early 1950s could actually measure a correlation on those timescales. But the logic was the same. If two photomultiplier tubes, separated by some distance, were pointed at the same star, the fluctuations in their outputs should be correlated, and the correlation should fall off with increasing separation in a way that encodes the star's angular diameter. There was one more thing going for the idea, and it is the thing that makes it beautiful in hindsight, though at the time it was perhaps the clearest reason to try. The correlation is measured after detection, electronically, in terms of timing, not in terms of optical path length. You are not trying to hold a physical path to a fraction of a wavelength. You are counting coincidences between two electrical signals, comparing when both tubes registered a flicker, and whether they did so together or independently. The atmosphere can shake and shiver and bend the light all it wants. As long as both tubes are still seeing the same star, the timing correlation will be there, unchanged. The phase corruption that destroyed Michelson's fringes is completely irrelevant to this measurement, because phase is exactly what has been thrown away. That was the power of it. That was why Hanbury Brown believed it would work where the great beam on the Hooker telescope had struggled. He and Twiss built a small experiment to test the principle at optical wavelengths. Not a telescope, not a great instrument on a mountaintop, a laboratory bench at Manchester. They took a mercury-arc lamp, a source that emits light in discrete spectral lines, bright and stable and well characterized, and they isolated its 435, 8 nanometer line, the vivid blue-violet line that a mercury lamp puts out with particular intensity. They split the light from this source with a half-silvered mirror, sending one copy to one photomultiplier tube and another copy to a second photomultiplier tube. The two tubes were both looking at the same source, the same lamp, through two separate optical paths, and they measured the correlation between the fluctuations in the two photocurrents. They looked at whether, when the output of one tube briefly rose, the output of the other rose too, slightly more often than pure chance would predict. And there it was, a positive correlation. When one tube saw the brightness nudge up, the other did too, not always, but more often than random chance, and by a specific, measurable amount. The flickers kept in step. This was published in 1956 in Nature. The paper was titled, plainly and precisely, Correlation Between Photons in Two Coherent Beams of Light. Hanbury Brown and Twiss were satisfied. They had shown that the correlation technique worked in the optical domain. The path to stellar diameters was open. What they had perhaps not fully anticipated was the storm that was about to arrive, not from the sky above, but from the physics community around them. Because when the result was announced, a number of serious and eminent physicists looked at what Hanbury Brown and Twiss had done, and they said, with complete confidence, that it was wrong. Not probably wrong. Not doubtful. Impossible. The measurement could not show what it claimed to show, and there had to be an error somewhere. The argument against it was not sloppy. It was rooted in real physics, and it is worth taking the time to feel it properly, because the story is much more interesting if you understand what the doubters were actually saying. They were not being foolish. They were applying a picture of light that was in many ways well supported and internally consistent. Here is the argument. At low enough light levels, a photomultiplier tube does not respond to a smooth wave of light arriving continuously. It responds to individual photons. A single photon arrives, it knocks an electron out of the tube's surface. That electron gets amplified, and you get a click. The photon is indivisible. You cannot split a photon into two halves and send one to each tube. A photon either goes to tube 1 or it goes to tube 2, not both. Now, if a photon is indivisible and each photon goes to only one tube, how can there be a correlation between the two tubes? The correlation would require that somehow, when tube 1 gets a photon. Tube 2 is also slightly more likely to get a photon at that same moment, but if the photons are going to separate tubes, each going to only one, how would tube 2 know that tube 1 just got one? The photons on this picture arrive independently, one at a time, each one ignorant of the others. There is no way for them to be correlated. Any apparent correlation must be an artifact of something else, a systematic error, a quirk of the electronics. And moreover, this was the deeper version of the argument. The correlation Hanbury Brown and Twiss were claiming seemed to require that two photons, one at each detector, could be related to each other in a way that looked uncomfortably close to violating the uncertainty principle. The phase of a photon and its photon number are related by a kind of uncertainty relation, and the correlations seem to demand too much simultaneous knowledge of both. These were real arguments. The people making them were not arguing from ignorance. They were applying a well-developed quantum picture of light and finding that by their reckoning the effect should not exist. In 1956, two physicists named Brannen and H. Ferguson published a note in Nature reporting that they had attempted to reproduce the Hanbury Brown and Twiss correlation and had found nothing. A null result. And they stated, in print, that if such a correlation did exist, it would be in contradiction with the principles of quantum mechanics. That is a serious claim. A result in contradiction with quantum mechanics is not a surprise or an anomaly. It is an error. Hanbury Brown and Twiss were in a position that is uncomfortable and clarifying in equal measure. They had a real, measured effect, carefully checked, supported by mathematics they believed was correct, in a technique already proven at radio wavelengths. And a segment of the physics community was telling them that what they had measured was impossible. Into this moment stepped Edward M. Purcell. Purcell was a physicist at Harvard who had won the Nobel Prize in 1952 for his work on nuclear magnetic resonance, the technique that eventually became MRI. He was not a man who needed to prove himself, and he was not a man who could be easily brushed aside. He read the controversy in Nature, and he wrote a short reply, crisp and unhurried, and what he said was this: the correlation is not just allowed by quantum mechanics, it is expected. It follows directly from the statistics that govern photons. Photons are bosons. That word may be familiar to you, or it may not. Bosons are particles with a particular mathematical character. They belong to a family of particles whose quantum states can be populated by multiple particles at once, particles that in fact slightly encourage each other to pile into the same state. Electrons are not bosons. Two electrons actively resist occupying the same state, which is why matter is solid and does not collapse. But photons are bosons, and the statistical rules for bosons, Bose-Einstein statistics, mean that when a photon finds itself in a particular mode, the probability of another photon entering the same mode is slightly higher than it would be otherwise. What this means for thermal light, light from a hot source, a lamp, a star, a flame, is that the photons do not arrive evenly spaced in time, like an army marching in perfect step. They arrive in clumps. They tend to come in pairs and small groups, with gaps of varying length between them, because the quantum statistics of bosons gently nudge them toward occupying the same temporal mode. This is photon bunching. And this bunching is exactly what the Hanbury Brown and Twiss experiment measured. When one tube detected a photon, the other tube was slightly more likely to detect one too, at the same moment, because photons from a thermal source, the mercury lamp, preferentially arrive in pairs. Not always, not dramatically, but measurably, by the specific factor that the theory predicts. The normalized correlation, what physicists now call G squared at zero time delay, equals 2 for perfectly thermal light. You are twice as likely to detect two photons at the same instant as you would be from a source that sprayed them out with perfectly random timing. Twice as likely. That is not a subtle effect, if you know what to look for. Purcell's argument was concise and beautiful and correct. And it has the particular satisfaction of a reply that not only defends the original claim, but explains why the objection arose in the first place. The doubters had been thinking of photons as independently fired billiard balls, each one ignorant of the rest. But photons from a thermal source are not like that. They are quantum particles obeying Bose-Einstein statistics. And their tendency to bunch is a direct consequence of that. It is not mysterious. It is not a paradox. It is simply what bosons do. Hanbury Brown later recalled, in his memoir Boffin, that distinguished physicists had told him the effect could not exist. He described the reception of the result with a mixture of bemusement and affection, the way a traveller might recall a storm that nearly capsized them, but seemed, in hindsight, to have been exactly as dramatic as the story required. The doubts were sincere, the resolution was satisfying, and the measurement, it turned out, had been right all along. There is something worth sitting with for a moment before we move on. The idea that photons from a hot source arrive in clumps, that thermal light is bunched in time, that if you catch one photon, you are slightly more likely to catch another right behind it. This is not something most people learn when they first meet the concept of light. It does not appear in the description of a light bulb or a candle or a star, and yet it is there, in every thermal source, quietly true, woven into the fabric of how photons behave. The mercury lamp on the laboratory bench in Manchester in 1956 was saying this about itself with every flash of its blue-violet line. And it took Hanbury Brown and Twiss and the argument that followed them to make the physics community slow down long enough to hear it. The laboratory result proved the principle. The correlation was real. The technique was sound. The next question was whether it could be scaled up, whether you could take this tabletop demonstration and turn it into something that could actually stand under the open sky and measure a real star. And the instrument that would do that was not going to be a telescope in the usual sense. It was going to be something stranger and more particular. But before we arrive at Narrabri, before we meet the two crude mirrors on their circular railway in the Australian dust, there is one more piece of the foundation to set in place. One more property of the technique, a specific and important one that explains not only why it works, but why it works when Michelson's method runs out of road. Remember what Michelson needed: two optical paths held equal to a fraction of a wavelength of light. Remember why the atmosphere destroyed him. Each layer of air, each thermal eddy and drift and shimmer, shifted those path lengths randomly and continuously, jiggling the fringes, making the contrast impossible to measure reliably. Now consider what Hanbury Brown and Twiss needed instead. They were not measuring fringes, they were measuring coincidences. Moments when both detectors registered a brightness peak at roughly the same time. They were measuring how well the two intensity fluctuations kept in step. And this required only that the fluctuations arrive at both detectors at almost the same moment. That the two detectors were sampling the same coherence patch of the source at the same time. The atmosphere bends and distorts the phase of light. It does not, on the short timescales relevant to intensity fluctuations, significantly change when a coherence patch arrives. The timing of the clumping, the bunching, the moment when a cluster of photons comes through, that timing is scrambled by the atmosphere far less than the phase is. And since intensity interferometry correlates timing rather than phase, it is largely immune to what the atmosphere does. This is the superpower of the method, and it is also its price, because you have thrown away the phase, and the phase carries information too. Without phase, you can recover the magnitude of the coherence, how strongly the two detectors agree, but not its sign, not the full complex character of the wave field. You recover less information per photon than Michelson's amplitude interferometer does. You need many more photons to build up the same statistical certainty. You need bright sources, very bright ones, and you need a lot of collecting area, big mirrors or lenses to gather enough light. Hot blue stars, it turns out, are ideal for this. They are bright. They radiate powerfully at short wavelengths toward the blue end of the spectrum, which is exactly where photomultiplier tubes of the era were most sensitive. And they are the stars whose angular diameters nobody could reach with the Michelson method, because they are small and distant in apparent size, requiring baselines of hundreds of meters to kill their fringes. Intensity interferometry could reach those baselines because it did not need to hold paths to sub-wavelength precision over those distances, and it needed bright blue sources, which hot stars precisely are. The two needs fit together like a key and a lock. The technique was made for exactly the stars that the previous method could not touch. That recognition was what made the project worth building. Not just as a proof of principle, not just as a clever idea on a laboratory bench, but as a real instrument, permanent and capable, designed to systematically measure the stars that had never been measured. An observatory dedicated to this one strange purpose, correlating flickers. It would be built in the southern hemisphere. The southern sky contains some of the brightest hot stars accessible from Earth. New South Wales, Australia, offered the dry, dark skies and the flat land needed for what Hanbury Brown had in mind. And what he had in mind was unlike any telescope that had ever been built before. But that is where we are going next, the details of it, the specific design. The two mirrors on their track, the numbers behind them, that is the next part of the journey. For now, settle back wherever you are and let this part rest. Michelson stood on his California mountain and held starlight steady for a fraction of a wavelength, and the atmosphere fought him, and he won just enough to crack the problem open, a handful of red giants measured, a technique proven, a limit reached. Then, a man from radio astronomy and his mathematician collaborator took the measuring problem apart at its roots, rebuilt it from signals and statistics and the natural tendency of thermal light to bunch, and proved in a Manchester laboratory that the new method could see something the old one never could. The physics community said it was impossible and had a real argument for thinking so. The argument fell apart. And in the falling apart, something new and unexpected was found, something that had been hiding in plain sight in every thermal light source in the world, every lamp and every star, waiting for someone to look at the right thing in the right way, long enough to hear what the light was saying about itself. So, let us go into the laboratory. Manchester, 1956. And I want you to picture it not as some grand cathedral of science, not gleaming halls and polished floors and hushed reverence, but as the kind of room that doing physics in the middle of the 20th century actually demanded. A workbench, cables going here and there with the confident untidiness of people who know exactly what each one is for. Bits of equipment that had been built or rebuilt or adapted from something else entirely. A mercury-arc lamp sitting at one end of the arrangement, glowing with that particular blue-white light that Mercury makes. The kind of light that has a faint, slightly industrial quality to it, as though it is slightly too interested in being noticed. Robert Hanbury Brown and Richard Twiss were trying something that, on the face of it, was almost absurdly simple, and that simplicity, it turned out, was exactly what made it so controversial. The mercury arc lamp produced a broad spread of wavelengths as most thermal light sources do. But they were not interested in all of it. They isolated a single, very specific line in the mercury spectrum, a narrow band of blue light at 435.8 nanometers. If you have ever seen the spectral lines of Mercury in a physics demonstration, that particular blue-violet line is one of the sharpest and most distinctive. They extracted it cleanly, leaving the rest of the lamp's output behind. Then they took a half-silvered mirror. A half-silvered mirror is exactly what it sounds like. It is a piece of glass coated so thinly with metal that half the light that hits it passes straight through and half of it bounces off at a right angle. Beam splitters, people call them, and they are workhorses of optics, the kind of thing you find in interferometers, in cameras, in all sorts of precision instruments. Hanbury Brown and Twiss used theirs to divide the beam of filtered mercury light into two paths. At the end of each path, they placed a photomultiplier tube. A photomultiplier tube is a beautiful piece of engineering in its own right. Light strikes a sensitive surface called a photocathode, and if the light is energetic enough, if an individual photon carries enough energy, it knocks out a single electron. That electron is then accelerated by an electric field and strikes a second surface, knocking out several more electrons. Those electrons are accelerated again, strike another surface, knock out still more. The cascade multiplies, stage by stage, until from that single photon you have produced a tiny but measurable pulse of electrical current. Photomultiplier tubes let you detect light with extraordinary sensitivity, down to the level of individual photons if you need to go there. They turn light into electrical signals. And electrical signals can be measured, recorded, compared. Hanbury Brown and Twiss connected their two photomultiplier tubes to an electronic correlator, a circuit designed to compare the output currents from each tube and measure whether the fluctuations in those two separate signals bore any resemblance to one another. Were they rising and falling at the same moments? Were they in step? Or were they independent? The prediction, according to the conventional wisdom of the time, was clear: the fluctuations should be independent. The beam splitter had divided the light into two separate beams. The photons hitting tube 1 were not the same photons hitting tube 2. Each photon, by the standard picture, was its own indivisible quantum, hitting one detector or the other, but not both. There was no physical mechanism by which the random variations in the count rate at one tube should be related to the random variations at the other. They should be doing their own separate, uncorrelated things. The correlator should read essentially nothing. What it read instead was a positive correlation. When the brightness of the light hitting one tube flickered up slightly, the brightness hitting the other tube flickered up at the same moment. When one went down, the other went down. The two independent detectors, pointed at the same light source through a half-silvered mirror, were marching in step. Not perfectly. There was noise, there was scatter, as there always is in real measurements, but the correlation was unambiguous. Clear, reproducible, they published the result in Nature in 1956. The paper was called, precisely and modestly, Correlation between Photons in Two Coherent Beams of Light. And it opened a storm. But before we get to the storm, let us sit with the result for a moment, because it deserves to be understood, not just reported. What Hanbury Brown and Twiss had found was this: thermal light, the light produced by a source at some temperature, the light that a mercury lamp makes, the light that a star makes, any light that comes from the random thermal jiggling of atoms, does not arrive at a detector in a perfectly even metronomic stream. Photons are not spaced out neatly like beads on an abacus. They arrive in clumps. If you imagine a stream of raindrops, not falling from a steady, uniform drizzle, but from the kind of shower where the drops sometimes come thick and fast, and then briefly thin out, and then thick again. That is closer to the texture of thermal light than the perfectly even tick-tick-tick we might naively imagine. The photons from a thermal source tend to arrive together, bunched, more often than pure chance would lead you to expect. Physicists gave this tendency a name, photon bunching, and they gave it a number, 2. There is a quantity called the second-order coherence, written as g squared of 0, or in the notation that became standard, g to the power of 2, evaluated at a time delay of 0, meaning you're looking at whether 2 photons arrive at the very same instant. For a perfectly random stream of photons, the kind a laser produces, as it turns out, this number is equal to 1. Random arrival, no bunching, no tendency to cluster. But for thermal light, for the chaotic light of a hot lamp or a star, the number is 2. G squared of 0 equals 2. What that means is that you are twice as likely to detect 2 photons arriving simultaneously as you would be from a perfectly random stream of the same average intensity. The photons are grouping. They are bunching together. You are more likely to catch them in twos than you should be by chance. This is not a small effect, and it is not subtle. It is a factor of 2. It is large. It is right there in the data if you look for it in the right way, and Hanbury Brown and Twiss had built exactly the apparatus needed to look for it. Now, where does this bunching come from? Why should thermal light be lumpy in this way? The answer lives in a piece of physics that Planck and Einstein and Bose and Einstein again had built up in the early 20th century, a framework that goes by the name of Bose-Einstein statistics. It is the statistical rulebook that governs the behavior of particles called bosons. Photons are bosons. And bosons have a peculiarity that distinguishes them sharply from the other class of particles. Fermions, electrons, protons, neutrons obey a rule called the Pauli exclusion principle. No 2 identical fermions can occupy the same quantum state at the same time. They push each other away in a quantum sense. Bosons have no such rule. In fact, they have the opposite tendency. Bosons are gregarious. They like to be in the same state as one another. They enhance each other's probability of occupying the same state rather than excluding it. This tendency shows up in an astonishing variety of places. It is why lasers work. It is why superconductors carry current without resistance. It is why Bose-Einstein condensates. Clouds of ultra-cold atoms that all collapse into the same quantum state can be made in the laboratory. In all of these cases, the bosonic nature of the particles is what allows them to bunch, to pile up, to cooperate. In the case of thermal light, the photons are bosons following Bose-Einstein statistics, and the consequence is that they arrive in clumps. The g squared of 0 equals 2 is not an accident. It is the precise, quantitative fingerprint of bosonic statistics applied to a chaotic thermal source. Hanbury Brown and Twiss had not found a curiosity or an artifact. They had measured a fundamental property of light. But the physics community was not ready to accept that. The objections that came back were not the objections of people who simply refused to believe something new. They were the objections of people who had thought hard about quantum mechanics and who had a specific reasoned worry. Let me try to lay it out the way it looked to the physicists who were troubled by it. Because their discomfort was not stupid. It was exactly the kind of careful, principled skepticism that good physics requires. Here was the concern. A photon in the standard picture is an indivisible quantum of light. When it hits a beam splitter, one of 2 things happens. It goes through, or it reflects. It does not split. It does not go both ways. It chooses one path, and that choice is made probabilistically, but once made. The photon is in one arm of the apparatus and not the other. So the photon that ends up at detector 1 and the photon that ends up at detector 2 are different photons. Completely separate events. Now, the correlation that Hanbury Brown and Twiss claimed to have measured seemed to say when a photon hits detector 1, photons are more likely to be hitting detector 2 at the same moment. But how? The two events involve different, independent photons. There is no physical connection between them. For them to be correlated, the photons would have to have some kind of prior agreement, some way of knowing about each other, and that seemed to violate the basic independence of quantum events. Worse, it seemed to brush uncomfortably close to questions about hidden variables and quantum entanglement, the kind of territory that in 1956 was still deeply murky and contested. And some physicists felt that if you pushed the argument hard enough, the claimed correlation would run afoul of the uncertainty principle, which sets precise limits on how well you can know the properties of a quantum system. In 1956, the same year Hanbury Brown and Twiss published their positive result, two other physicists, Brannen and H. Ferguson, published their own experiment in Nature. They had attempted to replicate the correlation measurement and had found nothing. A null result. No correlation. And they went further. They argued that a real correlation of the kind Hanbury Brown and Twiss claimed would in fact be incompatible with quantum mechanics. Not just surprising. Incompatible. This was a direct challenge, and it carried weight because it appeared in Nature, because Brannen and Ferguson were serious scientists making a serious argument, and because the theoretical basis for the Hanbury Brown and Twiss result was not yet clearly laid out. The experimental positive and the experimental null were sitting there side by side in the same journal, in the same year, and the field did not yet have the language to say with certainty which one was right. The reply came from Edward M. Purcell. Purcell is one of those figures in 20th century physics who seemed to find the essential thing wherever he looked. He had won the Nobel Prize in Physics in 1952, sharing it with Felix Bloch for the development of nuclear magnetic resonance, the same physics that underlies the memory scanners in hospitals today. He was not a man given to making errors about fundamental quantum mechanics, and what he wrote, in a brief but absolutely decisive note in Nature, was essentially this: of course, thermal photons bunch. It would be strange if they did not. His argument was clean and elegant. Bosons, particles with integer spin, of which photons are the archetypical example, have a natural statistical tendency to cluster in the same quantum states. This is not a mystery, and it is not a paradox. It is a theorem. It follows directly from the mathematics of Bose-Einstein statistics, which had been worked out and verified in many contexts long before Hanbury Brown and Twiss came along. The bunching is not a sign that photons are somehow communicating with each other or violating their independence. It is simply the statistical consequence of being bosons. When you have a thermal source producing photons in many modes simultaneously, the random beating of those modes causes the intensity to fluctuate, and those fluctuations have exactly the statistical character that produces g squared of 0 equal to 2. Not as a paradox, as an expected result. The null result of Brannen and Ferguson turned out to have a simpler explanation. They had not had sufficient time resolution in their detector system to see the very short duration correlations that the effect produces. The correlation is real, but it exists only within a very narrow time window, the coherence time of the light, which for a filtered spectral line like the Mercury 435.8 nanometer line is extraordinarily short. Their apparatus had smeared it out. They were, in effect, using a clock too slow to catch the tick. Hanbury Brown later wrote about this period in his memoir, which he called boffin, a word the British use for a scientist or technical expert, with a slight flavour of affectionate eccentricity about it. He recounted how distinguished physicists had told him, flatly, that his effect could not exist. He described the difficulty of having a result that felt solid, felt measured, felt right, and yet facing the insistence of people whose opinions deserved respect that the whole thing was mistaken. It was not a comfortable position. But he had the data, and eventually, with Purcell's theoretical clarification making the prediction precise, the data won. What Purcell had done in that brief Nature note was give the controversy the language it needed. He named the bunching, framed it in terms of Bose-Einstein statistics, and showed that the correlation was not an anomaly but a direct, unavoidable consequence of what photons are. The argument that it violated quantum mechanics had the matter backwards. It was quantum mechanics itself, specifically the bosonic character of photons, that predicted and demanded the correlation. The question was not whether Hanbury Brown and Twiss had broken physics. The question was whether the doubters had thought through what Bose-Einstein statistics actually implied for a stream of thermal photons. They had not. Or not completely. And that was understandable. These were not simple implications. The connection between the statistical nature of bosons and the visible, measurable bunching of photons in a thermal beam was not something that had been carefully worked through before Hanbury Brown and Twiss forced it to the surface. In that sense, their experiment did not just measure something. It compelled the field to think about something it had been quietly overlooking. Now, there is a subtlety here that is worth resting with for a moment, because it is one of the most interesting things in this whole story, and it is often glossed over. The photon bunching that Hanbury Brown and Twiss measured, the positive correlation, the g² of 0 equals 2, the tendency of thermal photons to arrive in clumps, can actually be explained without appealing to quantum mechanics at all. Without photons, without any graininess in light whatsoever. That sounds strange, but it is true, and Hanbury Brown himself was always careful to say so. If you treat light as a purely classical electromagnetic wave, a continuous, smooth wave, with no graininess, no photons, no quantum anything, and you let that wave have random fluctuations in its amplitude, then the intensity of the light will fluctuate randomly, and those intensity fluctuations will be correlated across the two paths of a beam splitter. The correlation comes from the fact that both paths are seeing the same underlying wave, and the same wave means the same fluctuations. A classical wave model predicts a positive correlation just as well as the quantum model does. This is not a failure of the quantum explanation. It is a sign that in this particular experiment, classical and quantum descriptions agree. The correlation is real either way. It exists in the data regardless of which framework you use to describe it. The bosonic bunching of photons and the classical beating of random wave modes give the same mathematical answer. They are, in a deep sense, different languages describing the same physical fact. Hanbury Brown understood this, and he was precise about it. He never claimed his experiment proved that light was made of photons, or that it demonstrated some irreducibly quantum property of nature. The intensity interferometer was a beautiful instrument for measuring angular diameters. It rested on the statistical properties of thermal light, and those statistical properties happen to be perfectly consistent with both classical and quantum descriptions. This matters because it means the controversy was, in a certain sense, double-layered. On one layer, the critics were simply wrong, the bunching is real, the correlation exists, Bose-Einstein statistics predicts it, and Purcell showed this clearly. On a second, deeper layer, the critics were wrong in a more interesting way. They assumed the effect was so quantum, so tied to the indivisibility of the photon, that it violated physics. But the effect does not actually require photons to be indivisible or to know about each other at all. It requires only that the light have the statistical properties of a thermal source, which can be described classically. The photon-centric objection turned out to be based on a misunderstanding of what the experiment was actually measuring. The truly non-classical story, the place where light does something that cannot be explained by any classical wave, no matter how carefully you model it, was still 20 years in the future. But we are getting ahead of ourselves. We will find that story when we reach it, and it will be worth finding. For now, the mercury lamp and the half-silvered mirror and the 2 photomultiplier tubes in Manchester have done what they needed to do. They have shown that the flicker correlation is real, they have shown that it survives the scrutiny of serious physics, and they have demonstrated, in a tabletop arrangement far removed from any telescope or mountain or observatory, the basic principle that Robert Hanbury Brown needed to take his measuring idea to the sky. And this is the right moment to look at what that measuring idea actually gives you, mechanically, when you remove it from the heat of controversy and hold it up quietly in the light. The key to the whole thing is what happens when you move your 2 detectors apart. In the Manchester experiment, the 2 photomultiplier tubes were, in effect, looking at the same spatial patch of the light beam. They were both illuminated by the same source through the beam splitter, and they both saw the same thermal fluctuations because the coherence patch of the filtered mercury light was larger than the separation of the effective apertures. That is why the correlation was strong. Now imagine instead that you are looking not at a lamp on a bench, but at a star. And instead of 2 photomultiplier tubes side by side, you have 2 separate detectors spaced some distance apart on the ground. Both are pointed at the same star. Both are recording the way the star's light flickers, not the dramatic twinkling caused by atmosphere, but the deeper, subtler intensity fluctuations that are intrinsic to the thermal character of the starlight itself. And you correlate those fluctuations electronically, just as Hanbury Brown and Twiss did in Manchester. If the 2 detectors are very close together, say a metre apart, they are sitting within the same coherence patch of the starlight. The thermal fluctuations arriving at detector 1 and arriving at detector 2 are the same fluctuations, because both detectors are being illuminated by light that is still spatially coherent across that small separation. The flickers are in step. The correlation is high. Now move the detectors apart. 10 meters, 50 meters, 100 meters. At some point, the detectors are too far apart to be sitting within the same coherence patch. The light reaching detector 1 and the light reaching detector 2 have come from slightly different angles on the star's face, and the thermal fluctuations from those slightly different angles are no longer perfectly in step. The correlation begins to fall. Move them further, and the correlation continues to fall. And at some specific separation, some baseline, the correlation effectively reaches 0. The 2 detectors are flickering completely independently. The starlight at one is doing nothing related to what the starlight at the other is doing. That baseline, that distance, that is the measurement. Because the size of the coherence patch, the distance over which the starlight's thermal fluctuations stay in step, is set precisely by the angular size of the star as seen from Earth. A star that subtends a larger angle on the sky has a smaller coherence patch because light from different parts of its disk is arriving at different angles and washing out the coherence more quickly. A star that is very small in apparent size, barely more than a geometric point, has a very large coherence patch. Its fluctuations stay correlated over large distances because essentially all of its light is coming from the same direction. So you measure the correlation as a function of baseline separation, and you find the distance at which the correlation fades. That distance tells you the angular size of the star, not an image, not a resolved disk, not fringes, just a number, the baseline where the agreement between two independent flicker records dissolves, and from that number you infer the true angular diameter of the star you are looking at. This is the Van Sittert-Zernike theorem at work, the same mathematical backbone shared by Michelson's amplitude interferometer and Hanbury Brown and Twiss's intensity interferometer. Both methods are measuring the coherence of starlight across separated points. Michelson measured the coherence of the electromagnetic field itself, the amplitudes, the phases, the actual wave shape. Hanbury Brown and Twiss measured the coherence of the intensity fluctuations, the envelope of the wave, the brightness variations, stripping away the phase entirely and working only with the magnitude of the coherence. And stripping away the phase is exactly where the power comes from. Because phase is the thing the atmosphere destroys. When Michelson was trying to hold his fringes steady on the 100-inch Hooker telescope, every tiny ripple in the air above Mount Wilson introduced a tiny variation in the time it took the light to travel down each arm of his beam. Those tiny variations shifted the phase of the light reaching the combining point, and they shifted it randomly, and they shifted it fast. Faster than he could track them, faster than he could compensate. The atmosphere was continuously, relentlessly perturbing the phases of his two beams, and those perturbations smeared his fringes and reduced his visibility and capped the baselines he could use. Hanbury Brown and Twiss's method did not use phase at all. The electronic correlator did not care about the phase of the light at either detector. It cared only about whether the intensity at one detector went up when the intensity at the other went up, and whether it went down when the other went down. Whether the light wave was currently in a peak or a trough. Whether the atmospheric turbulence had introduced a quarter wavelength shift or a half wavelength shift in one arm was entirely irrelevant. The correlator was blind to phase. It was measuring the envelope, the brightness variation and the atmosphere, while it could scramble the phase, could not scramble the envelope on the timescales relevant to the measurement. The atmosphere could make the light arrive later. It could not make it arrive brighter or dimmer at the frequencies relevant to the intensity correlation. Those brightness fluctuations, the thermal bunching of the photons, the clumping that Purcell had identified as the natural consequence of Bose-Einstein statistics, propagated through the air without the atmosphere being able to corrupt them in a way that would destroy the correlation. The measurement was, in a precise technical sense, immune to the thing that had made Michelson's life so difficult. This immunity was not an accident. Hanbury Brown had understood it from the beginning, because the same immunity was what made intensity interferometry work in radio astronomy. Radio waves have wavelengths thousands of times longer than visible light, and the corresponding requirement to hold two receivers in phase is therefore correspondingly more demanding in some ways and less demanding in others. But the same fundamental issue of atmospheric and cable length stability had motivated the intensity correlation approach in the first place. Back when Hanbury Brown was thinking about Cygnus A and Cassiopeia A in the years around 1949 to 1952, when he and Twiss ported the idea to visible light, the immunity to phase scrambling came along as part of the method's nature. But nothing is entirely free. The immunity to atmospheric phase perturbation came at a price, a significant one. When Michelson combined the light from his two subapertures, he was bringing the electromagnetic field itself to a point and interfering it. Every photon that arrived at the combining point contributed constructively or destructively to the fringe pattern, and the signal he was building up was proportional to the amplitude of the light, which is to say, to the square root of the intensity. The fringes were bright. They were visible. They could, in principle, be followed and measured even when the light was not particularly dazzling, because amplitude interferometry is efficient. It uses the light well. Intensity interferometry correlates fluctuations, and fluctuations are, by nature, small. The intensity of a beam of light is not wildly variable from moment to moment. It fluctuates by small amounts around its mean value. The correlation you are trying to measure is a correlation between those small fluctuations. To measure a small correlation reliably, you need a great many measurements. To make a great many measurements quickly enough that you can get a useful answer in a reasonable observing time, you need to be collecting a lot of photons per second, which means you need a very bright star or very large collecting areas, or both. The signal-to-noise ratio in intensity interferometry is far more demanding than in amplitude interferometry. For a given telescope size and a given star brightness, Michelson's method gathers a much stronger signal. Hanbury Brown and Twiss's method, in exchange for its immunity to the atmosphere and its freedom to use baselines of any length, had to pay with sensitivity. It could not see faint stars. It needed sources that were flooding its detectors with photons, bright, hot, blue stars that poured out light in the wavelengths the photomultiplier tubes could detect. This limitation shaped every aspect of the great instrument that Hanbury Brown was planning to build in New South Wales. The collecting areas would need to be large, the wavelengths would need to be short, because hot blue stars are brightest in the blue and the ultraviolet. The electronics would need to be fast and sensitive, and the targets would be chosen from the brightest, most luminous blue-white stars accessible from the southern sky. But those constraints also defined, quite precisely, a scientific program that nobody else had managed to carry out. Michelson's amplitude interferometer had measured a handful of the largest red giants, Betelgeuse, Antares, Arcturus, Aldebaran, the hot main sequence stars, the blue and white luminaries that are among the most important stars in the sky for understanding stellar evolution and the structure of the galaxy, were too small in angular size for Michelson to resolve. Intensity interferometry, with its long baselines unconstrained by the atmosphere, could go where amplitude interferometry could not. That was the gap, that was the scientific territory waiting to be mapped, and it was precisely the territory the new instrument in New South Wales was designed to enter. But there is one more thing to understand about the technique before we go south, and it is connected to the question of what, precisely, the Manchester Mercury lamp experiment actually proved, and what it left open. When Purcell wrote his reply to Brannen and Ferguson, when he showed, cleanly and briefly, that Bose-Einstein statistics naturally predicts the bunching of thermal photons, and that the correlation is therefore not a paradox, but an expected result. He was answering one question. He was saying, yes, the correlation is real, yes, it is consistent with quantum mechanics, and here is the framework that explains it. That was the essential vindication. But the vindication came with a subtlety that Hanbury Brown was always careful to preserve. The thermal bunching effect, the positive correlation, the g² of 0 equals 2, is not proof of the quantum graininess of light. It is not something that only a photon model can explain. You can derive the same g² of 0 equals 2 from a purely classical wave model, treating light as a continuous field with random fluctuations, and you get the same answer. The photon picture and the wave picture agree here. They are two descriptions of the same phenomenon. This is actually a precise statement about where the boundary of classical and quantum descriptions of light lies. Classical electromagnetic waves, with random phases and amplitudes drawn from a thermal distribution, produce intensity fluctuations that have exactly the same statistical character as the clumping of bosons following Bose-Einstein statistics. The mathematics is the same. The predictions are the same. You cannot tell from a thermal bunching measurement alone which description is more fundamental. What sits on the other side of that boundary, what classical waves genuinely cannot produce, no matter how you model them, is the opposite effect. Not bunching, but anti-bunching. Photons arriving more evenly spaced than a random stream, a g² of 0 less than 1. Less than 1 means you are less likely than chance to catch two photons at the same instant. The photons are, in a sense, avoiding each other. No classical wave can produce that. A classical electromagnetic field, fluctuating randomly or smoothly or in any combination, always produces intensities that satisfy g² of 0 greater than or equal to 1. To get below 1, to get into the anti-bunching regime, you need a source that is genuinely quantum in its character, a source where the very discreteness of the photon, the indivisibility of the quantum of light, actively structures the arrival pattern. In 1956, anti-bunching had not been observed. The instrument and the theory and the specific sources needed to produce it were not yet in hand. What Hanbury Brown and Twiss had found was real, was significant, was correctly explained by Purcell, and was the start of a chain of thinking that would eventually lead physics there. But the truly impossible for classical physics result was still waiting, 2 decades away. For a different experiment with a different source and the language to describe it that did not yet exist. For now, the mercury lamp in Manchester had served its purpose. The positive correlation was measured. The objections had been answered. The tabletop had demonstrated the principle that Hanbury Brown needed to make the transfer from idea to instrument. It is worth pausing here, in the quiet of the laboratory, and noticing something. The whole arc of this episode in physics, the confusion, the null result, the controversy, the Purcell reply, the gradual acceptance, happened very fast. The positive result was in Nature in 1956. Brannen and Ferguson's challenge was also in 1956. Purcell's reply was also in 1956. In the span of a single year, the effect was announced, contested, and substantially vindicated. The physics community processed this quickly, not because it was simple, but because the tools for thinking about it, Bose-Einstein statistics, the mathematics of quantum fields, the framework of quantum mechanics itself, were already in hand for anyone who looked carefully enough. Purcell's note in Nature is, if you read it, a remarkably compact thing. It does not require a long argument. It requires, essentially, that the reader take Bose-Einstein statistics seriously and apply it to the case of a stream of photons from a thermal source. Once you do that, the bunching follows immediately. It is a deduction, not a hypothesis. The correlations that Hanbury Brown and Twiss measured were, in hindsight, already implicit in the structure of quantum mechanics as it stood in 1956. No new physics was needed to explain them. What was new was looking for them. What was new was building an apparatus sensitive enough and fast enough to see them. What was new was the specific, precise measurement that forced the existing theory to be applied to a case it had not been applied to before. And that, quite often, is where science actually advances. Not always through the discovery of entirely new laws, but through the recognition of what the existing laws already implied in a domain nobody had looked at carefully. The mercury lamp in Manchester was not a new phenomenon. It was a lamp. The photomultiplier tubes were standard instruments. The correlator was electronics ingeniously applied. The new thing was the question Hanbury Brown and Twiss were asking of the light, and the care with which they asked it. The star they were about to ask it of was Sirius, the brightest star in the night sky, save for the sun. A hot, white-blue main sequence star, the kind of star that Michelson could never reach, the kind of star that had sat just out of range of the best amplitude interferometry for 35 years since Betelgeuse was measured on that December night in 1920. And for that measurement, they would leave Manchester and move to a place where they could set up something larger. Something better suited to pointing at a specific star and holding both detectors on it long enough to accumulate the correlation signal they needed. But the principle was settled. The controversy had done its work, and the work it had done was to make the foundation solid. Purcell had built the floor beneath the idea. What remained was to stand on it and look up. They drove the equipment north of Manchester first, to Jodrell Bank, and they set up something you would not immediately recognise as a precision astronomical instrument. 2 ex-military searchlight mirrors, the kind that had spent the war scanning the sky for enemy aircraft, sweeping great arcs of light through the dark. Not instruments built for delicacy, not polished to the exacting tolerances of a research telescope. They were tools of a different era, pressed into entirely new service, pointed now not at a plane, but at a star. And not a large, cool red supergent, like Betelgeuse, the kind of star that Michelson's instrument had been barely able to reach. These mirrors were pointed at Sirius. Sirius, Alpha Canis Majoris, the brightest star in the night sky after the sun. A hot, white-blue star on the main sequence, young and fierce, burning at a surface temperature far above that of our own mild yellow star. It blazes so brightly that on a clear night it seems almost to push back at you, too bright to look at directly for long. Shifting colours at the horizon as the atmosphere bends and disperses its light. And it is, in angular terms, tiny, its apparent disk, if you could even call it a disk, which ordinary telescopes absolutely cannot, spans something like 0.0069 arcseconds across the sky. That number is worth sitting with for a moment. Betelgeuse, the star Michelson measured in 1920, is a red supergiant so swollen with age and burning that its diameter exceeds the distance from the Sun to the Earth. Its angular size, as seen from here, is around 0.047 arcseconds. Even that is smaller than the blur the atmosphere spreads across starlight. But 0.047 is at least a number the amplitude interferometer could chase. Fringe visibility dropped measurably as the baseline grew, and the fringes, shimmering and nervous as they were, could be watched and recorded with sufficient patience. Sirius at 0.0069 arcseconds is another thing entirely, nearly 7 times smaller in apparent size. A baseline of more than 100 meters would have been needed to see the fringes from Sirius wash away. 100 meters of rigid, sub-micron stable optical path, held steady through atmospheric boiling, sustained long enough to accumulate data. Nobody had done it. Because in any practical sense nobody could. Not with amplitude interferometry. Not then. But with the searchlight mirrors, 2 of them, aimed at the same star and connected only by electronics. By a wire along which fluctuation signals could be compared, the atmosphere did not matter in that way. The mirrors did not need to be optically coupled. The light from each one went straight into a photomultiplier tube, was converted to an electrical signal, and the comparison happened in the correlator. The atmospheric shimmer that ruined Michelson's fringes was, to this instrument, a kind of background noise it simply stepped over. Because it was not looking for the phase of the light, it was looking for the tempo of the brightness. And brightness fluctuations, the random clumping of photons that Purcell had so cleanly accounted for, arrived at both detectors in a way that the atmosphere could perturb a little, but could not destroy. The coherence patch, that region over which the light's fluctuations stayed in step, was determined by the star's true size on the sky, not by the turbulent column of air the light had passed through to reach the Earth. And when they ran the correlation, when they set up the 2 searchlight mirrors at a known separation, pointed them both at Sirius, and let the correlator count, they found what they expected and feared would not be there. A positive correlation. The flickers agreed. At the separation they had set, the light from Sirius still arrived in step at both mirrors, the photon bunching synchronized across the baseline, the little clumps of light reaching each detector in patterns that were, within the measurement's precision, not independent but related. They moved the mirrors apart, and as the baseline grew, the correlation shrank. They had measured Sirius, not by forming an image, not by combining the light into interference fringes and watching the fringes fade, by correlating the flickers, by watching 2 independent shimmers of starlight and measuring precisely how far apart you had to sit before those shimmers stopped keeping time together. The angular diameter they derived was approximately 0.0069 arcseconds, a star 7 times smaller in apparent size than what had been considered the outer limit of direct angular measurement. A star that Michelson could not touch, a star that had sat beyond reach for 35 years. Through all of the careful work at Mount Wilson, through the frustrations with the 50-foot beam that warped and trembled and eventually defeated Pease. A star that a pair of surplus searchlight reflectors and an electronic correlator measured at Jodrell Bank by asking not what the light was, but when it arrived. And now something became clear that had perhaps not been entirely obvious at the tabletop scale. The technique worked, not just on a bench lamp, not just on photomultiplier tubes a metre apart, staring at a controlled source. It worked on a real star, at astronomical distances, with detectors set tens of metres apart in a field, under a night sky, using equipment that was blunt and repurposed, and nothing like the refined instruments of precision optics. It worked because the principle was correct, and because the principle did not depend on anything fragile. It did not depend on optical alignment to a fraction of a wavelength. It depended on timing, and timing was something electronics could do. That knowledge, once in hand, opened a question. If you built something properly, a real instrument, designed from the start to do this, built at a site chosen for its clear skies and its open space, how far could you push it? Robert Hanbury Brown, with Richard Twiss, and with the team that gathered around them, began to think about what a purpose-built intensity interferometer would look like. And what they designed was, in its way, magnificent, the Narrabri Stellar Intensity Interferometer. New South Wales, Australia, a site chosen for its dark skies, its long clear nights, its southern latitude that opened up regions of the hot young stars of the southern sky that were difficult or impossible to observe from Britain or from Mount Wilson in California. They broke ground in the early 1960s, and the instrument was operational somewhere around 1963 and 64. What you would have seen if you had driven out to Narrabri and looked across the flat ground in the daylight were two reflectors. Not polished mirrors in the traditional sense. Each one was 5 meters in diameter, and each one was built from 252 hexagonal mirror segments fitted together into a curved collecting surface. 252 separate pieces assembled into a dish. And here is where it gets interesting. And a little wonderful. Those mirror segments did not need to be figured to high optical precision. They did not need to bring starlight to a sharp focus. They did not need to form an image at all. They only needed to collect light, to gather photons from the star and funnel them toward a photomultiplier at the focus. The optical quality that would be the obsession and the expense of a conventional telescope was simply not required. The mirrors were deliberately crude by the standards of a research observatory, and that was fine. That was the point. The information was not in the image. The information was in the rate of arrival of the photons, in the timing of the clumps, and a rough mirror gathered those photons just as honestly as a perfect one. Each of those two reflectors sat on a trolley, and those trolleys rode on a circular railway track. The track was 188 meters in diameter, nearly 200 meters across. A circle of rails out in the New South Wales countryside, and the two trolleys with their 6.5-metre dishes of hexagonal mirror segments could be positioned anywhere around that circle, pointed at the same star, and run at any separation from just a few metres to the full diameter of the track. Moving them changed the baseline, and changing the baseline moved you across the coherence patch, the region of agreement in the star's flickering light. If the star's angular size produced a coherence patch that was 50 meters wide, say, then detectors separated by less than 50 meters would see correlated flickers, and detectors separated by more would not. The instrument did not need to know the phase of the light. It did not need to be calibrated to a fraction of a wavelength. The railway track was the ruler, the baseline was the variable, and measuring how the correlation coefficient fell as the baseline grew, sweeping out the coherence function, gave you the angular diameter of the star directly. This is the measurement. This is what all the controversy and all the mercury lamps and all the searchlight mirrors in Manchester and all the Purcell one-page rebuttals had been building toward. Two rough dishes on a circular track in rural Australia, both pointed at the same hot star, both feeding their photon arrivals into a correlator and the number that came out. the baseline at which correlation dropped to half of its maximum, or the shape of the curve as the baseline swept. That number, translated through the Van Sittert-Zernike theorem and the known wavelength of the light, gave you the star's true angular width on the sky. They measured 32 stars, 32 stellar angular diameters, most of them hot. Blue. Main sequence or near main sequence stars, O-type and B-type and A-type stars, the young, brilliant, searingly hot stars that burn fast and bright and that radiate powerfully at the short blue wavelengths where intensity interferometry works best. This was a deliberate choice. The technique's weakness was sensitivity. Correlating intensity fluctuations is photon for photon, far less efficient than combining the light directly. To get a measurable signal, you needed very bright sources. You needed short wavelengths, where the coherence effects are easier to resolve with a given baseline. And you needed patience, long integrations, night after night, accumulating the correlation. Hot blue stars provided all of that. They are bright. They radiate heavily in the blue. And in the southern sky visible from Narrabri, there were enough of them, and they were well placed enough to build what had never been built before, a systematic empirical catalogue of stellar diameters. Before Narrabri, the effective temperature and angular diameter scale for hot main sequence stars was theoretical, inferred, computed from models of stellar structure and spectral type. Nobody had measured them directly. There were too few angular diameter measurements to anchor the scale. Betelgeuse and Antares and Arcturus and Aldebaran, a handful of large, cool, nearby giants, were the whole observational base, and those are about as representative of the general stellar population as a redwood is representative of a suburban garden. After Narrabri, there was a catalogue. Hanbury Brown and his colleagues Davis and Allen published it in 1974. 32 hot stars with direct angular measurements, direct estimates of effective temperature and linear diameter built from those measurements combined with distance information. A scale, an empirical foundation. Not a model, a measurement. And then the instrument stopped. Not because it had failed, not because the technique had been discredited, it stopped because of the same trade-off that had been written into the design from the beginning. Intensity interferometry throws away phase, it requires bright sources. And as astronomers began to ask questions about fainter stars, about stars further away, about stars of more modest luminosity, about the enormous variety of the stellar population, the technique, as built at Narrabri, could not follow. The instrument's sensitivity was the limiting factor. The biggest, brightest, hottest stars had been measured. The next tier was darker, and the signal-to-noise ratio fell faster than could be compensated for by simply waiting longer. By the early 1970s, the instrument had done what it could. By somewhere around 1972 to 74, it was decommissioned. A technique born in controversy, vindicated by Sirius, expanded across 32 stars, and then quietly set aside. Not wrong, not defeated, simply waiting for something to change. But before we follow that waiting, there is something else that happened in the years when Narrabri was running. Something that was perhaps even more consequential than the stellar diameters themselves. Because while Hanbury Brown and his team were measuring the widths of hot stars in New South Wales, something was churning in the world of theoretical physics, a quiet upheaval. And it had been started, without entirely meaning to, by the Mercury lamp in Manchester. Roy J. Glauber was a physicist at Harvard. Trained as a theorist, steeped in quantum mechanics from its foundations, a careful and precise thinker who had worked on fundamental problems in quantum field theory and statistical mechanics. He had followed the Hanbury Brown and Twiss controversy closely, and it had bothered him in a productive way. Not because he thought the experiment was wrong. He understood Purcell's argument. Boson's bunch, that was correct. But he felt, with the particular unease of a theorist looking at a working result, that the theoretical language available to describe what was actually happening was not quite right. Not quite complete. The existing framework for describing light was built for first-order coherence, for amplitude correlations, for the interference phenomena that Michelson had exploited, that Young's double slit had demonstrated, that optical physics had been organized around for generations. The coherence measured by those experiments was first-order coherence, the correlation of the field amplitude at different points or times. And that framework was mature and powerful and well understood. But the Hanbury Brown and Twiss effect was something different. It was a correlation not of the field amplitude, but of the intensity, the square of the amplitude. It was what Glauber would come to call second-order coherence. And the existing theoretical machinery was not built to describe it cleanly, to place it within a consistent quantum mechanical framework, to distinguish it from other possible correlation effects in a rigorous way. So Glauber built the machinery. In 1963, he published his quantum theory of optical coherence. It was not one paper, but a series of them, and together they constructed a formal language for describing the statistical properties of light at every order. First-order coherence, GIL, which captured the amplitude correlations and the interference phenomena, the Michelson fringe visibility, the Young's slit pattern. Second-order coherence, GIL, which captured the intensity correlations, the Hoped effect, the bunching, and higher orders beyond that, extending the hierarchy as far as you needed to go. Within this language, the different kinds of light could be precisely distinguished. Ordinary thermal light, the light of a glowing filament, a mercury-arc lamp, a star, has GEs equal to 2. Twice as likely to detect 2 photons at once as you would be from a random Poissonian stream. Bunched, clumpy, this is what Hanbury Brown and Twiss had measured and what Purcell had explained. It follows directly from Bose-Einstein statistics, from the fact that photons are bosons and bosons prefer to travel together. But Glauber went further. He identified a different kind of light, a kind that he called coherent. The ideal coherent state is, in quantum mechanical terms, an eigenstate of the photon field operator, and it has a g-nears of exactly 1. Its photons arrive with the statistical regularity of a Poissonian process, random, but not bunched, not clumped, not enhanced in simultaneous arrivals. This is the light produced, to very good approximation, by a laser. It sits in between thermal light, which bunches more than random, and something else that had not yet been observed, something else that Glauber's framework predicted must exist, even though nobody had seen it. Light with a g-nears less than 1, more evenly spaced than random, anti-bunched. Photons arriving in a stream where, if one photon has just arrived, the next one is actively unlikely to arrive immediately after. A stream where the photons in some sense keep each other at a distance in time. He called this regime non-classical, because no classical electromagnetic wave, no matter how you manipulate it, can produce a g-nears below 1. The mathematics of classical wave fields has a hard flaw. Random fluctuations in a classical field give you exactly 1. Bunching can go above 1. But sub-Poissonian, anti-bunched light, that is forbidden in classical wave theory. It requires a description in which the discreteness of the photon is not a convenient approximation, but a fundamental constraint on what can happen. Glauber's framework placed the Hochbit result in a larger map. It showed where the star measurement sat relative to the full landscape of possible optical correlations, and it identified the unexplored territory that lay just beyond. This framework, this hierarchy of coherence functions, this language of coherent states and correlation orders became the foundation of a new field: quantum optics. Not a rebranding of classical optics with a quantum footnote, but a genuine new discipline concerned with the quantum statistical properties of light, with how light really behaves when you look at it carefully enough, at the level of individual photons and their arrival times, rather than at the level of smooth, continuous electromagnetic waves. Leonard Mandel and Emil Wolf were central to what that field became. Mandel in particular worked on the experimental side of the photon statistics that Glauber's theory described, developing sensitive measurement techniques, pushing the precision of photon counting experiments, and contributing to the deepening understanding of how quantum mechanics constrains what light can do. The field that the controversy over a mercury lamp and 2 photomultiplier tubes had helped open became, through the 1960s and 70s, one of the most productive and surprising corners of physics. And in 2005, the Nobel Prize in Physics was awarded, in part to Roy J. Glauber, for his contributions to the quantum theory of optical coherence. He shared the prize with John L. Hall and Theodor W. who received their portions for work on laser precision spectroscopy and the optical frequency comb. 3 different threads of physics brought together in one year's prize, and one of those threads ran straight back to the controversy over 2 photomultiplier tubes staring at a mercury-arc lamp in Manchester in 1956. Now, there is something I want to set before you carefully, because it is the kind of thing that the standard telling of this story tends to glide past, and in gliding past it, it misses something genuinely important, something that makes the story richer, not thinner. Here is the thing. The Hanbury Brown and Twiss effect, the bunching of thermal light, the positive correlation of photon arrivals at 2 detectors is, in the end, fully explainable by classical electromagnetic wave theory. Let that settle for a moment. What Purcell showed is that Boson's bunch. Yes, but there is another way to see the same result that does not invoke photons at all. Thermal light is not a smooth, continuous wave. It is a superposition of many independent wave components with random frequencies and phases, and those components beat against each other. The beats produce random fluctuations in the total intensity, the speckle pattern in time. When 2 detectors are within the coherence length of the source, they are both seeing the same beat pattern, and so their fluctuations are correlated. When they are further apart than the coherence patch, the beat pattern at one is different from the pattern at the other, and the correlation drops away. This is a classical wave argument. It does not require photons. It does not require quantum mechanics. It requires only that light is a wave with random components, and the mathematics of those random components produces exactly the correlations that were measured. Hanbury Brown understood this very well. He wrote about it explicitly. He was not a man who wanted to claim more than the data showed, and what his experiment showed was that correlations existed, that they were well described by the wave theory, and that the photon picture, Bose-Einstein statistics, gave the same answer from a different starting point. 2 consistent pictures of the same phenomenon. He was quite clear in his memoirs and in his technical writing that the effect did not prove that light was quantum. It was consistent with both descriptions. The genuinely quantum result, the one that the classical wave picture cannot explain, the one that has no classical analogue and sits on the other side of the GI's Cull-1 boundary, is antibunching. Photon antibunching. The observation that photons, in certain circumstances, arrive more regularly than random. That GI's is less than 1. That if you have just detected a photon, you are less likely than chance to detect another one immediately afterward. This is classically forbidden. No wave intensity, however you manipulate it, can drop below the Poissonian floor. Antibunching is the smoking gun. It is the result that says, without equivocation, we are not dealing with a classical wave here. We are dealing with something that has a genuine, irreducible discreteness. Something that must be described at its foundations by quantum mechanics. And antibunching was first observed in 1977. Not in a star, not in an astronomical instrument. In a laboratory by H. Jeff Kimball, Mario Dagenais and Leonard Mandel, yes, the same Leonard Mandel who had been central to quantum optics from its early days. The source they used was resonance fluorescence from a beam of sodium atoms. A sodium atom, when it absorbs a photon and then re-emits one, cannot emit a second photon until it has absorbed another. It has a built-in refractory period. It is physically impossible for two photons to emerge from the same atom in 0 time. The G-nears must be 0 for a perfect single emitter. And when Kimball and Dagenais and Mandel measured it, using an instrument that was, in its essentials, a descendant of the HB correlator, 2 detectors, and an electronic correlator measuring coincidences, they found just that. G-nears was below 1. The photons were antibunched. That observation, in 1977, closed a loop that had been open since the Mercury lamp in Manchester 2 decades before. Glauber's framework had predicted a non-classical regime. Kimball, Dagenais and Mandel found it, and what they found it with was a refined version of Hanbury Brown and Twiss's own apparatus, the logic of the correlator, the coincidence measurement, the comparison of 2 detectors' signals. The experts who had said it was impossible in 1956 were wrong, but the story of how they were wrong is more interesting than the legend usually has it. They were wrong not because they failed to understand quantum mechanics, but because they applied their understanding of quantum mechanics too narrowly. They thought the correlation would require photons to act in ways that violated their individual independence. What they missed, what Purcell saw, and what Glauber formalized, is that quantum statistics does not require individual photons to communicate. It requires only that they obey the rules of bosons. And bosons, by the rules of bosons, bunch, not because they know about each other. Because they are indistinguishable, and indistinguishable particles obey different counting rules than distinguishable ones, and those counting rules favor coincidence. The bunching is not a signal passed between photons. It is a property of the ensemble, a statistical shadow cast by the quantum nature of identical particles. And the antibunching that Kimball and Dagenais and Mandel observed in 1977, that is the other face of the same coin. Also a statistical property. Also a consequence of the quantum rules. But this one with no classical face at all. This one visible only when you look at the world as it really is, at the level where the smoothness of waves breaks down and the graininess becomes unavoidable. So the story has a deeper shape than it appears to. The Hoped effect opened quantum optics not by proving light was quantum in some simple sense, but by creating the pressure. The experimental challenge, the nagging question of what exactly was going on, that forced the development of a language precise enough to say what quantum and classical actually mean for light statistics. And once that language existed, it pointed directly to phenomena that were genuinely and irreducibly quantum. The antibunching that came 20 years later, and the applications, diverse and surprising, that have come in the decades since. Consider where the same logic has travelled. In particle physics, the correlations that Hanbury Brown and Twiss saw in starlight have an exact analogue in the collisions of heavy atomic nuclei. When gold atoms or lead atoms are fired at each other at velocities approaching the speed of light, the collision produces a fireball of extraordinarily hot, dense matter. For a fraction of a second, conditions exist that have not existed since the very early universe, and then the fireball expands and cools and the particles fly outward in all directions. Among those particles are identical pions, mesons, bosons, particles that obey the same Bose-Einstein statistics that photons obey. Those identical pions, produced from the same source, are correlated in exactly the HBT way. Pairs of pions with similar momenta are more likely to be detected close together in momentum space than random chance would predict. And the shape of that correlation as a function of the separation in momentum encodes information about the size and lifetime of the fireball from which they came. A measurement that has nothing to do with stars. Performed in the largest and most expensive particle colliders ever built, reads out a spatial scale using the same mathematical machinery that Hanbury Brown and Twiss developed to measure Sirius. The stellar-size ruler became a subatomic fireball ruler. And closer to home, in the everyday world of laboratories working on quantum cryptography and quantum computing. In research groups that may be thinking about practical applications of quantum mechanics, not about the night sky at all, the Dagenais correlation measurement that Hanbury Brown and Twiss pioneered is now a standard diagnostic test. When you build a source that you claim emits single photons, one at a time, never two at once, the way you verify that claim is to run the hoped correlator. You split the output of your source onto two detectors. You measure coincidences. You compute G. If it is below 1/2, your source is genuinely quantum. If it is at or above 1, you have a classical source pretending. The two surplus searchlight mirrors in a field at Jodrell Bank and the railway track at Narrabri and the philosophical argument about whether Sirius could give a measurable signal, all of that is now baked into the test that researchers run before they trust a single photon source with the secrets they are trying to protect using quantum keys. The technique did not disappear. It changed shape. And in astronomy itself, the intensity interferometer is being revived. The detectors built to study very high-energy gamma rays from astrophysical sources, the imaging air Cherenkov telescopes, the instruments that catch the faint blue flash of Cherenkov light when a high-energy gamma ray slams into the Earth's upper atmosphere, those instruments are large. 6.5 meters is modest compared to what has been built since Narrabri. The Veritas Array in Arizona consists of 4 telescopes, each 12 meters in diameter. The Magic telescopes on La Palma in the Canary Islands are larger still. And at those sites, in experiments published around 2019 and 2020, astronomers demonstrated that intensity interferometry still works, that you can point these large instruments at bright hot stars, run electronic correlators between them, and measure stellar angular diameters with the same logic Hanbury Brown and Twiss established. The baseline's available now because the telescopes are spread across whole observatory sites rather than confined to a circular track of 188 meters, are far larger. And the future is larger still. The Cherenkov Telescope Array, an international project that will spread telescopes across sites in Chile and La Palma, is designed partly with stellar intensity interferometry in mind. Baselines reaching kilometers. Angular resolution finer than any optical amplitude interferometer currently operating. The technique that was shelved in the early 1970s because it could not reach faint enough stars is returning with instruments vast enough to compensate, and with electronics fast and precise enough that the correlators of the 1960s look, by comparison, like mechanical clocks beside an atomic standard. What could not be done in 1974 will be done. Different stars, different questions. But the same logic, unchanged, two detectors, a distance apart, recording the shimmer of a star's light, and the distance at which the shimmer stops agreeing is the star's true angular size. Lie still for a moment and think about what that means. There is a star, somewhere up there, beyond the ceiling, beyond the roof, beyond the thin membrane of air that holds the world together. A star so far away that the fastest thing in the universe would take years to reach it. From here, it appears as a point of light. Not because it is small in any absolute sense, it may be hundreds of times larger than the Sun. A furnace that would swallow the inner solar system without noticing, but because it is so far away that its disk is measured in thousandths of a degree. No lens, no mirror, no image can show you that disk. The atmosphere alone blurs your view by more than the disk is wide. And yet, two detectors, set a distance apart, pointed at that same star, recording only numbers, fluctuation rates, photon counts, the random timing of light's clumps and gaps, can extract from those numbers a measurement of the star's true angular size. They do not see it. They feel it, in the rhythm of the light's randomness. Because the randomness is not perfectly random. It is correlated, and the range of that correlation is set by the star's apparent disk. And the range of that correlation is a ruler, and that ruler can be read. The size of a star is hidden in the way its light flickers. That is the sentence this whole story was trying to reach. Not in the brightness, not in the colour, not in the Doppler shift or the absorption lines. In the flicker, in the random, moment-to-moment shimmer of intensity that every star produces, because its light is not a smooth, continuous wave, but a statistical process. Photons, bosons, particles of a field that arrives in faint clumps rather than in perfect order, and those clumps carry a spatial fingerprint of the source that produced them. The fingerprint is subtle, measurable only with care and precision and the right kind of question. But it is there. It was always there. It was there in the light of Sirius when Michelson was measuring Betelgeuse. It was there in the light falling on Jodrell Bank, on Narrabri, on every dark field where someone thought to ask the right question. You have been listening to this, wherever you are, with a window somewhere nearby, perhaps, and the dark outside it, and the stars above the dark. If it is a clear night and you happen to look up and you see a point of light that does not twinkle in quite the same way as the others, that flickers fast and blue and refuses to resolve into anything you can measure with your eyes, you might think of what is hidden in that flicker. Not just photons from a burning nuclear furnace 6 light-years away, or 60, or 600, but a geometry, an angular diameter encoded in the correlation of its random clumps, waiting for someone patient enough to read it with two separate eyes, set 100 meters apart, and the electronics to compare what each one sees. The experts who said it was impossible were not stupid. They were asking the right questions in the wrong direction. They wanted to protect the principle that photons do not communicate, and they were right to want that. But they had not yet understood that the correlation does not require communication. It requires only that the photons come from the same source through the same coherence patch, and that bosons are bosons, indistinguishable, and indistinguishable in a way that has measurable statistical consequences. Purcell understood it. Glauber formalized it. And what Glauber formalized was not just an explanation of the HBT effect, but a new language for all of quantum optics, a language in which thermal light, coherent laser light, and the anti-bunched light of a single atom could be precisely described and distinguished and measured. The mercury lamp in Manchester was not meant to start a field, it was meant to win an argument. And it won the argument, and in winning it, it opened something much larger. Because the argument was about something fundamental, about what light is, about whether the discreteness of photons has statistical consequences that are measurable, about whether the randomness in quantum mechanics is structured or plain, and answering it required building the theory to the depth it needed. Glauber built that theory. And from that theory came a discipline that now underpins quantum, cryptography, and quantum computing, and the precision measurement of stars, and the sizing of fireballs in heavy ion colliders, and the testing of single-photon sources in laboratories that would not exist if a pair of searchlight mirrors had not been pointed at Sirius on a night in the mid-1950s. All of that from two correlating flickers, from asking not what the light is, but when it arrives, and how consistently two separate arrivals keep time with each other. If you are still with me, you have travelled a long way tonight. From the problem of a star that would not show its face, a point of light, no disk, no edge, no size that any image could reveal, through the beautiful, frustrated, atmosphere-tortured attempt of Michelson and Pease at Mount Wilson with their 20-foot beam and their shimmering fringes, through the radio astronomy that gave Hanbury Brown and Twiss the seed of the idea. Intensity correlation applied first to radio sources, Cygnus A and Cassiopeia A, before it ever came near an optical telescope. Through the tabletop mercury lamp, the 435.8 nanometer blue line, the half-silvered mirror, the two photomultiplier tubes, the positive correlation that nobody expected and many refused to believe. Through Purcell's single-page reply in Nature, patient and elegant, showing that of course bosons cluster, you should expect exactly this. It falls out of Bose-Einstein statistics. It is not a paradox, but a consequence. Through Sirius, measured at 0.0069 arcseconds by ex-military searchlight mirrors at Jodrell Bank. Through the circular railway at Narrabri, two crude 6.5-meter dishes built from 252 hexagonal segments, grinding slowly around their 188-meter track, measuring 32 hot blue stars and building an empirical scale that had not existed before. Through Glauber at Harvard, building the full quantum theory of optical coherence, the G and Dagenais hierarchy, the coherent states, the language that placed all of this inside a rigorous framework. Through the honest complication that thermal bunching is classically explainable, and the genuinely non-classical result, antibunching, GIL below 1, photons more regularly spaced than chance allows, came later, in 1977, from Kimball and Dagenais and Mandel in sodium atoms in a beam. And through the modern descendants, fireballs in particle colliders, gamma-ray telescopes in Arizona and the Canary Islands proving the technique still works, and the G-Nilus measurement as a daily diagnostic in the laboratories trying to build the quantum computers of the next generation. It is a long arc, and it bends towards something simple and strange. That the size of a distant thing, a thing too far away to ever see clearly, can be read from the way its light randomly varies, if you know what to look for and how to measure it. That information about the large is encoded in the small. That the graininess of light, the fact that photons arrive in faint clumps rather than in a perfect smooth flow, carries a spatial signature of the source that made them. That two separate detectors, comparing notes about their independent shimmers, are reading a coherence pattern written into the light itself by the width of the star that sent it. You didn't need to hold on to every number. The numbers were the scaffolding. The idea is the thing that stays. A flicker, a correlation, a baseline, a star. If you enjoyed this slow journey tonight, a gentle like or subscribe means a great deal. Small channels like this one rely on your support to keep these quiet journeys going. And if you'd like to share where you're listening from tonight and what hour it is in your corner of the world, I'd be glad to know. There is something I find quietly wonderful about the thought of people in different time zones, in different weathers, under different patches of sky, all having arrived here by the same route, looking for something slow and true to carry them toward sleep. The universe is not finished being strange. There is more to come, on other nights, at other slow paces. The story will keep until you wake. Sleep well, fellow voyager. The next journey keeps until you wake.